All right, fine. Let's look at 4.2. Write down the formula of solution X. Now, this is interesting because they told you that solution X is made up of an unknown nitrate. So I already know this solution X is dash nitrate. Now, what is this dash that's missing? Well, let's look at the metal that we're trying to use to electroplate the other. What metal are we trying to use to coat the other one? So we're trying to use copper, as you can see there underlined again. A cell that is used to electroplate an iron rod with copper. So copper is the important bit there. So that means the electrolyte has to be made up of a nitrate that contains the same metal that we're trying to use to coat the other. So in this case, this should be copper nitrate. Or we can write this symbol for copper nitrate, which is not that much of a big deal. All right, fine. So I guess we didn't, in the end, we didn't really need this table at the moment, but we are going to see the uses of that table later. So it is pretty important. Sometimes we want to specify which copper we're talking about. Now, in most cases, guys, I should add this to you guys. In most cases, we're dealing with copper 2 in most cases, because this is a more stable form of copper, especially if we're talking about making a solution out of it. It's a more stable solution. Rather, it's a more stable form of copper in a solution there, or whether when it's dissolved in water. I'm not sure dissolved is the right word to use there. All right, fine. Anyways, let's move on to the next bit. So if you wanted to specify this, you could actually write copper 2 all right, no, not there. Copper nitrate is the name of this. What I wanted you to say here is to write this as a formula. So we can write CuNO3 instead of writing the full word. Let's say you didn't want to do that. So the idea of this being copper 2 should come and assist us there to put a little bit of it too, just in case you forget what copper nitrate is all about. There is a table that we normally use during our live classes that kind of reflects how things bond to each other. So we've got copper 2 plus, which is the copper 2 I was talking about, and then NO3 minus, and then when they bond, the whole switching of these powers, this being a subscript of this one and this being a subscript of this one. So we just focus on the coefficients. The 1 comes here. This is what you have there. So we don't normally write that 1. And then the 2 goes there. We know all these rules from grade 10. You can revisit that if you need more information on that. But anyways, that was the answer to that. Let's move on to the next bit. So in this question, we've got which electrode A or the iron rod is the negative electrode. This we have already done this. Okay, we've already answered that, and we know the electrode that's negative should be the iron rod. Okay, so what's left is for us to figure out the reason. Well, the iron rod is negative. Why? Well, because reduction occurs there. Or here, whatever the case you want to say there, whatever you want to say. All right, fine. Let's look at this one more time. We say this is a negative terminal so that it can kind of attract the positive ions, copper ions, so that it can reduce them. That's the secret behind that. So that's why we say reduction happens here as a reason for why we think this should be negative. All right. But otherwise, I've explained why and how we ended up having the negatives and the positive sign on the other stuff. So let's move on to the next bit. Write down the half reaction that takes place at electrode A. So if we check out our electrode A one more time, is the copper electrode, is it? And we said oxidation is happening here. So that shouldn't be too difficult. So we're looking for copper. Let's find our copper 2 to be specific. So where is my laser pointer there? Right. Let's look for copper 2. I've got copper 1 here. Like I said, if we didn't specify to you, or the question doesn't specify, assume we're using copper 2. That's the most stable one. Unless, of course, the question strictly tells you we're talking copper 1. It's rarely used. Anyways, let's talk about this is the expression that this is the equation that I want, or rather the reaction that I'm looking for. So the way we're going to write this, let's be careful. We said we need to show what? Oxidation. So you're gonna write it from this side to that. Remember, oxidation is the increase in oxidation numbers, right? Or the loss of electrons. So you're gonna start from this side to that side. So what I have there is copper turning into copper 2 plus 2 electrons. Now this is telling you we are losing 2 electrons, and copper there, which was initially solid, has now been oxidized to a copper 2 plus ion, right, which dissolves in your liquid there, in your water rather. So you have an electrolyte. It's now part of the electrolyte now. That's why you write the aqueous there. Right, fine. If we think of it in terms of oxidation numbers, we've got an oxidation number of 0 up here and an oxidation number of 2 on the right. So there is an increase in oxidation numbers, which supports the definition of what we mean by oxidation. So that's the oxidation half reaction that we wanted to have there. Let's move on. Electrode A is now replaced with a silver rod without making any other changes to the cell. After a while, 2 metallic ions are found to be present in the solution. So let's go back again. Electrode A, instead of having this one as copper, we now have it as silver, which is Ag. All right. Now, obviously, oxidation is still going to happen on this side since remember our goal is to what? Is to electroplate this. So we want oxidation to happen on the silver. We want silver to lose electrons. And then if it loses electrons, that means it's losing a bit of its mass there. Some of its atoms lose their electrons, become ions, and then they want to be oxidized on the other side. So that's what we're saying. So with that in mind, let's come back and try to answer this question. It says, name the 2 metallic ions present in the solution. Right. Just to remind you of what I said. We said for our Ag there, we want oxidation to happen there, or the loss of electrons to occur here. If we lose an electron, if an atom loses an electron, then automatically that atom becomes an ion. It's no longer pure silver. So we now have Ag plus falling off of this, and that's how we lose the mass. Right, fine. Now that means we're gonna have some Ag ions in our electrolyte. And remember, previously we had copper, so we expect also to have some copper 2 plus ions in the electrolyte as well. So if we were to name the 2 metallic ions that are present, I think we've just gotten our answer. Is the silver ions and the copper ions. So again, you can try to write that in words if you feel like writing it. So copper 2 plus ions, whereas these are silver ions. All right, fine. Let's move on to the next bit. I can remove this now. Now, refer to the strength of oxidizing agents to explain which one of the two ions will preferably be involved in the plating process. Now, let's think about what we want to do on the other side when we are electroplating. So I'm now going to focus on this negative electrode where we are gaining the electron. Right, fine. So when we're gaining the electron, what process is going on there? Reduction. Okay, so we want to reduce whatever it is that's coming from the other electrode. So it could be copper 2 plus, or it could be the silver. So we want to see which one of these two is going to get reduced ahead of the other, or preferably get reduced. So let's remember our small phrases again, describing what an oxidizing agent is and what a reducing agent is. So let's start with the oxidizing agent. This is the substance that is reduced. Okay, and then a reducing agent is a substance that is oxidized. Okay, so let's think about that for a few seconds. What is reduced is called the oxidizing agent. What is oxidized is called a reducing agent. Now, if you check your table, it has got two arrows, one on the left hand side and one on the right hand side. If you check on one on the left hand side, it says it says increasing oxidizing ability, and the arrow points down. That means the lower we go on the left hand side, we're having stronger oxidizing agents. By stronger oxidizing agents, we simply imply that these will get reduced better than what we have up here, which should be weaker oxidizing agents. I don't know if I'm talking sense. So let's check out what's happening on the right hand side of this. And it says here increasing reducing ability. That means we're talking reducing agents. All right. Right, fine. So what we'll be having here is stronger reducing agent up here, and then weaker reducing agent down here. That means the higher we go up our table on the right hand side, we should expect to have something like a stronger reducing agent, which means these up here will get oxidized better than the weaker reducing agents. So in this case, what process are we looking to achieve? Right? What process do we want to focus on? We want reduction to occur because we want to coat this with some metal, is it? So we want reduction of either one of these two. So which one of these will be reduced better than the other? So like I said, a stronger oxidizing agent is reduced better than a weaker oxidizing agent. So what you want to check is between copper and silver, between these two ions that we have here, which of these ions is far down, rather, is a stronger oxidizing agent. So we check, let's search for our silver there real quick. Okay, so hope to find our silver real quick. Oh, there's copper. So I've located copper. Now let's find silver. If we go down, there is silver. All right, fine. So copper is clearly up here and silver is down there. So between these two, if I'm comparing them, copper is a much weaker oxidizing agent and silver is a much stronger oxidizing agent, right? So that means we expect silver to be oxidized more or better than copper. So as long as these two are still present in this electrolyte, we are always going to oxidize silver ahead of what? Of copper. I hope that makes sense. So that brings us to the solution there. That means we want to say which one of these will be preferably involved in the electroplating. So our answer is silver, because silver is a stronger oxidizing agent than copper. So I want to remove this a bit, write it on the other side. Uh, but I guess you get the concept. Stronger oxidizing agent. All right, fine. So there we go. That should be your solution there, and hopefully you understood that particular explanation and breakdown of what this was all about. Now, I want to end this here, and in the next smaller section, we'll be talking about exercise 6. Okay, and in this video, we're going to continue with our exercise. Now we're in exercise 6. The simplified diagram below represents an electrochemical cell used to refine copper.